Hello, everyone. Good morning here in Asia and good evening there in North America. Welcome. I'm Jet Aguilar from the Astronomical League of the Philippines, and I will be the host for today's webinar. Thank you for joining us for our 2023 Astronomy Expert Speaker Series online lecture. And I believe this is the 18th one that we are having. And we are so happy and proud to have with us today a fellow Filipino and a young brilliant physicist as our speaker. This is a much anticipated talk. So our speaker at a very young age had already made a name for herself with her outstanding accomplishments in academic science and mathematics. And she also has a very large social media presence and following because of her advocacies in science. Our speaker had even broken the record for the most number of registrants ever, 533 as of the latest count, for this Astronomy Expert Speaker Series of lectures since we started in 2022. The title of Miss Hillary's talk is Searching for the Oldest Stars and Galaxies in the Universe. My fellow ALP member, Miss Imelda Jozon, will be doing the introduction for our esteemed speaker. For those who were not able to register or could not log in anymore to this Zoom webinar but would still want to watch, we are currently live streaming on Facebook at the Facebook page of the Philippine Astronomy Forum. Before we start, kindly allow me to explain some rules for this webinar to help us make this an enjoyable learning experience for everyone. Please listen and do your best to give your undivided attention to our speaker. There will be a short question and answer session at the end of the lecture. You may type in your questions under the Q&A tab found in your Zoom interface at any point during the presentation. We will do our best to read and answer your questions live after the lecture or via the Q&A tab. We would like to remind everyone that the contents presented in this webinar will remain as the individual property of the lecturer and the photographers in the presentation. We will also be distributing certificates of attendance via email to all registered attendees who will be present with us throughout the webinar. So please use the name you have written in your registration forms to help us facilitate this process. So everyone sit back and enjoy the webinar, and let us all have fun learning. Here's the program flow for the webinar. And I would like to turn you over now to Mr. James Kevin T., the president of the Philippine Astronomical League of the Philippines, for his welcome remarks.
Thank you, Jet. Good morning to our viewers in the Philippines, and good evening to our guests in the United States and Europe. My name is James Kevin T., President of the Astronomical League of the Philippines. On behalf of the ALP, I would like to welcome you to our Astronomy Expert Speaker Series 2023. This webinar is part of our ALP's International Astronomy Educational Outreach Program. Our goal is to bring renowned experts and scientists to the Filipino people and to the rest of the world. This is why the webinar is being offered free to the general public. I would like to take this opportunity also to thank ALP members who are instrumental in putting up this program altogether, especially Imelda Johnson, Edwin Aguirre, Dr. Jet Aguilar, Jun Lau, Kendrick Colty, Andrew Ayan Chan, Peter Benedict Tobalinal, Eric Africa, and Justin Chan. So this will be our 18th lecture in the speaker series. Our speaker for today is no other than Hilary Diane Andales, Ph.D. student in astronomy and astrophysics in the University of Chicago, as well as a Filipino science communicator. We have more distinguished speakers lined up in the months to come. So without further ado, I'd like to turn over the introduction of the speaker to Imelda Joseph.
Thanks, James. And good morning and good evening to everyone. There comes a point in our lives when we need to pass the torch in our quest for knowledge to the future generation. Oftentimes in this speaker series, I've introduced speakers whom we've known for at least a couple of decades or more. Today is going to be very different. It is because Edwin and I just met our speaker last month. Thanks to our former Sky Telescope colleague, Kelly Beatty, who reached out to us to introduce Hillary. She will be the youngest speaker in our series so far, and she is still a student. She has a very impressive bio, and I could sense her enthusiasm while talking to her on the phone the very first time we spoke. It reminded me of both Edwin and myself during our teenage years. That is why, after that initial call, I spoke to Edwin about inviting her to be our speaker today. She doesn't just have a top-notch resume, but what impressed me most is her resilient and ambitious attitude that was so palpable during our conversation. She told me about her family's losses during Super Typhoon Yolanda. She was only 14 then, but losing everything didn't stop her from trying to reach her dream of aiming for the stars. She went on to get her high school education at the Philippine Science High School in the Visayas and joined competitions where she won a total of $400,000 in scholarships and funds for her high school science lab. Most teenagers would opt to spend their time hanging out with friends to go shopping, play video game, or spend much of the day chatting on social media. But Hillary is different. She instead invested her time planning the path to getting a quality college education, not just from any colleges or universities. Instead, she aimed high, choosing to go to the Massachusetts Institute of Technology, or MIT, a highly respected university here in the United States. A university whose graduates include many Nobel Prize winners, prominent scientists, astronauts, and engineers, the likes of Apollo 11 astronaut and second man on the moon, Buzz Aldrin, as well as Nobel laureates and astronomers Rainer Weiss, who predicted gravitational waves, and Adam Rees for discovering the acceleration of the universe's expansion. Just this year, Hillary earned her bachelor's degree in physics from MIT. Next year, she will be starting her Ph.D. program on astronomy and astrophysics at the University of Chicago. For her outstanding research on galactic archaeology, Hillary received the Barrett Prize and the Chambliss Medal. And while at MIT, she served as the president of the MIT Society of Physics Students. We are born in this world with many different interests, sets of skills, and different purposes. Some of us are good in the language of art, of business, finance, some in music, some in science, some in engineering, and some in the language of mathematics. Just like Hillary, we all need to find our purpose and aim to be good at it. For everything that we are able to accomplish in our careers and in our lifetime would be the foundation of the work that Hillary's generation will be using to continue our generation's legacy. Hillary is the future generation who will have to do what will be leaving behind unfinished. She will be an inspiration to the generation after her, who will one day have to continue her mission. Hillary is one young scientist the Filipino people can be proud to call a kababayan. Friends, let us welcome Hilary Diane Andales as our very first student to speak at our Astronomy Expert Speaker Series.
Thank you po. Thank you, Ma'am Imelda and Sir Edwin, and to all of the Astronomical League of the Philippines for inviting me this morning. Maraming salamat po. And I'm very happy to see everyone here attending, especially since ang daming mga Pinoy na andito. And I'm very happy to see na a lot of the attendees here are of my generation. And I hope that I can inspire you to appreciate astronomy more, because there are a lot of us, a lot of humans in the world who are interested in astronomy, and also surprisingly a lot of Filipinos. It's not very well known that marami palang Pilipino na may interest in astronomy, but there is a bustling community of Filipinos in astronomy, and that I find that very encouraging. Okay. So today, my talk will be basically about the research that I do on ultra-faint dwarf galaxies, or the oldest galaxies of the universe. So let me just start sharing my screen here. Anyway, okay. Can we all see the screen? All good. Yes. So, oh, my bad. Let's go back. Anyway, so going back from the beginning, today I will be sharing my research on the oldest galaxies of the universe. All of this has been work that I undertook as an undergraduate student in MIT, or the Massachusetts Institute of Technology. And of course, I did all of this through the help of my mentors, graduate student Dr. Kaylee Brower, and then my professor Anna Friebel. So basically, before I talk about my work, I want to talk about a brief history of myself, basically. So as Ma'am Imelda already mentioned in the introduction, I grew up in the Philippines, but I just wanted to show you some pictures of how I really grew into the person that I became today. So going back to 2004, 2005, you can see me in a little uniform as a student of Gabaldon Central School. So back then I was very tiny, and as a child, I was already extremely interested in the sciences. And a lot of that interest really came from the inspiration of my parents. My parents were they met in the University of San Carlos, and they had this very infectious curiosity about the world. So my dad finished chemistry and my mom finished accountancy, but even though they studied different fields, they had this mutual interest in the sciences. And back then, I grew up in Abuyog, Leyte, and we weren't doing well financially back then. But despite that, my parents really, really valued education. And as a result, kahit na, even though our house was very small, it was filled to the brim with books. My family really liked to buy used books. And in our home, they like to tell me stories. So instead of fairy tales like Cinderella and Sleeping Beauty, they would tell me stories about Charles Darwin and his adventures in the Galapagos Islands, or Albert Einstein and how his ideas changed the world, how his revolutionary ideas about the nature of space and time really changed the way we thought about the universe. And also about Marie Curie, who was such an amazing scientist, such a genius. And what made her even more awesome was how she broke down those barriers, and as a woman scientist during her time when science was such a male dominated profession, which it still is until now, but we're doing better. Anyway, so because of those stories, because my parents instilled in me the coolness of science, really, I found out about how these ideas could really change the world. I became really interested in pursuing science as a profession. And as a result of that, I kind of had it in the back of my mind that, oh, really, I should really be a scientist when I grow up. But this was very interesting considering how I didn't know any living scientists in my area. But anyway, proceeding to high school, I went to high school in Philippine Science High School. I started developing an interest in, when I was in elementary school, I had an interest in science and math. And when I went to high school, I thought that the most natural thing to do to combine those interests was to do physics. So when I came to college to MIT, it was kind of a no-brainer for me to declare physics as my major. And then when I was in MIT, I found my true love in astronomy. And as a result of that, I ultimately decided to choose to pursue a PhD in astronomy and astrophysics. And I chose to do that in U Chicago, which I will start in 2024. And how did I really get interested in astronomy? So I told you about my interest in science more broadly, but how did I get interested in astronomy? Well, it started when I was a kid. I was tiny, 5 years old, and my mom gave me this book called The Big Book of Space Discovery. And as a 5-year-old, this book was basically as tall as I am, but I really loved reading that. And on the very first page of that book was the picture, something like the picture on the right, where you could see a scale model of the solar system. And to me, this was such a shocker because, you know, when you kind of look up at the sky, the sun is tiny. Although, quick advice, do not look up at the sun directly. But when you look up at the sky, you kind of see that the sun is, you know, a small point. But when I saw this book for the first time, I was really shocked at how huge the sun was compared to the Earth. And in reality, you could fit 1 million Earths into the sun. And this was just what made me so interested in the study of the universe, how we could learn about the vast space in which we live in. And that's basically what fueled me to keep being interested in learning more about the universe. And then when I went to MIT, I was really lucky to have had the opportunity to really put my interest in astronomy into practice. And one of my most memorable things that I did was to take this class called Astrolab. And what we did was we had to propose our own project, and we could use the telescope that we wanted, and we had to operate it all by ourselves. So this was me operating the Elliott telescope in the Wallace Observatory that is owned by MIT. So I was inside this dome. I was the only person in there in the dead of winter, and I had to do all the operations by myself, and it was really cool, very memorable. And after that, I became even more interested in studying astronomy, specifically observational astronomy, which was why I took another class called Astronomy Field Camp, and MIT took us to the Teide Observatory in Spain, where we spent an entire month just doing our own kinds of research. And here is me in the control room of this telescope right here on the bottom right. And this is the what telescope is inside that dome. And this is on the top left, you could see a picture of me and my classmates there. So this was really the experience that cemented my interest in observational astronomy. I just thought that it was so cool that we got to live at the top of a mountain for a whole month and just do astronomy. It was very dark. All we had to do was to use the telescopes, analyze the data, and then hang out together. And I thought that that was such a nice life. And that was why I really decided to do observational astronomy for my PhD. So I just wanted to tell you that to give you kind of a glimpse into what life is like as a young aspiring astronomer. But now I want to pivot into what I actually do, which is I really seek to answer this one big question that humanity has never ceased to ask ever since, we started thinking about ourselves. And that question is, where did we come from? This is one of the grand questions that we really want answers for. This is the question of our origins. Where did we come from? Where did we as humans come from? Where did our world come from? Where did the stuff we're made of come from? And back then, when science wasn't really a thing, we had creation myths to try and make sense or try to figure out an answer to this question. And I would just want to refer to this old creation myth from Bukidnon, where they tried to make sense about where the moon and the stars really came from. So very quickly, the story goes that back then, the sky was close to the ground. And a spinster or a woman went out to pound rice. And before she began her work, she took off the beads from around her neck and the comb from her hair and then hung them on the sky, which at that time looked like a coral rock. And then she began working. And each time that she raised her pestle up into the air, it struck the sky. And for some time, she pounded the rice, and then she raised the pestle so high that it struck the sky very hard. Immediately, the sky began to rise, and it went up so far that she lost her ornaments, like the comb and her beads, and never did they come down, for the comb became the moon and the beads and the stars, and the beads are the stars that are scattered about. So this was kind of how we tried to make sense of the world back then. And obviously now we have come very far from these creation myths, but this just shows how, how primal this kind of question, our desire for answers to this question is. And in my research, I seek to answer a very similar question, except the question that I want to answer is not the origin of the moon and the stars. It's the origin of something even bigger than that. It's the origin of our home galaxy, the Milky Way. And just to give you a glimpse of the scale at which I try to answer that question, how big really is the Milky Way, I want to show you this video just to give you a perspective about the scale of the galaxy. So this is a video called Cosmic Eye, designed by an astrophysicist. Now we keep zooming out now we're off the, and then we keep zooming out. We're past the orbit of the moon, 1 million kilometers. We keep going till, near Earth asteroids. And we reach the asteroid belt. We're not even away from the solar system yet. Now we've reached our new horizon star. We're at cloud on the Kuiper belt at this point, and we're not even out of the solar system yet. So we keep going. Now we've reached our neighboring stars. We keep going, and so on and so on. And now we've reached our own corner of the Milky Way. And so here, we stop here, basically. So at this point, this is really the scale that I work in my research. I look at the Milky Way and its neighboring galaxies. And looking at this video, it really seems astounding how huge our own galaxy is and how, imperceptible we are at the scale of the galaxy, let alone the scale of the universe. So really, as I said before, my goal in my research is to reconstruct one grand origin story, which is how did the Milky Way form? And how do I do that? As I said earlier, I look at the Milky Way itself and its neighboring galaxies. And some of the galaxies that I look at, which are the galaxies in this picture right here. And you can see these two galaxies that are pictured in this panoramic view of the Milky Way from the southern hemisphere. So this is a picture from the Las Campanas Observatory in Chile. And so does anyone here know what the galaxies that are circled are? If anyone can quickly type it in the chat, I will give you 10 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay, does anyone have any idea? You can type it in the chat. Does anyone have any idea? Oh, let's see.
Magellanic Cloud.
Oh, there, I see. Mama Imelda said yes. Yes, so those are the Magellanic Clouds, exactly. So this one here is the Large Magellanic Cloud, and this one here is a Small Magellanic Cloud. And these are satellite galaxies of our Milky Way, which is an interesting idea. So just like how Jupiter has its own moons orbiting around it, the Milky Way also has its own galaxies orbiting around it or gravitationally bound to it. And these are just two of the galaxies that are orbiting around the Milky Way and that I use for my research. And so zooming out even further to what is really the map, what are the galaxies orbiting around the Milky Way? So we have all of these things here. So if we go back to the year. So this is a video of all of the satellite galaxies around the Milky Way that we've discovered so far. So this is a time lapse from the 1930s to 2019. So in the 1920s, 30s, all we knew were the Magellanic Clouds, the LMC and the SMC, large and small. And then we discovered Sculptor, Fornax, Ursa Minor, Leo 1, 2, Carina. And then very suddenly we have this explosion of new discoveries, the ones that are colored red and the ones that are colored green. And that is from, the Sloan Digital Sky Survey. And because of that, we now know that there are a lot of galaxies orbiting around the Milky Way. And these things that orbit around the Milky Way hold very big clues into how the Milky Way emerged. So what do these galaxies actually look like? A lot of the galaxies that you see from these NASA images are, these beautiful spiral galaxies with a lot of color and a lot of structure. You can see the spirals and the bars and so on. But these are not what the galaxies I work with look like. Instead, what they look like are this. They're kind of just like blobs of stars. Basically, if you look at a field of stars, they're just a clump. And even if you look at the least massive, if you look at the least massive of the galaxies here on the bottom row, they don't even look like a clump at all. They just look like stars, and it's not clear that they're even associated at all as a galaxy. But we do know that they are galaxies. If you look at their distances, and if you look at what they're made of, you can tell that they all come from this, they're all associated as one singular body. So all in all, these are the galaxies that I work with. Galaxies like Draco, Eridanus 2, and Pictoris 1, these are what I call the ultra-faint dwarf galaxy. And just to hammer home how ultra-faint and dwarf these galaxies really are, I invite you to look at this picture of Reticulum 2 here. And so this is a picture of a star field where Reticulum 2 is approximately located. But if I blink here, these are really the stars that are in Reticulum 2. So if you look at a field, that's not even the stars that are in Reticulum 2. These are the only ones that are in that ultra-faint dwarf galaxy. So it's really extremely small. The Milky Way has around hundreds of billions of stars. Meanwhile, these ultra-faint dwarf galaxies only have around tens of thousands. And what makes these ultra-faint dwarf galaxies special? Well, we call them cosmic fossils. Because they can tell us about our origins. So just like how, archaeologists and paleontologists use fossils to learn about the early Earth, we use cosmic fossils like these ultra-faint dwarf galaxies to learn about the early universe. So why are they called cosmic fossils? Well, they formed very early on in the universe in the first few billion years. And as a result of that, they're old. And because they formed in the first few billion years of the universe, they are metal poor. So how does that happen? Well, as you may have heard, the universe started from this Big Bang, and the Big Bang made a few elements. So hydrogen, helium, and a little bit of lithium. And as the first stars formed, they exploded. And when those first stars exploded, they made some of the heavier elements. And then after they exploded, they had these supernova remnants. They would spew out all of their gas into the galaxy. And then now that gas, few billion years after, that gas again clumps into another star. So that is the new generation of stars. And because these stars came from, the ashes of the first generation of stars, they now have more heavier elements, which are what we call metals in astronomy. And so as a result of that, we can kind of form this relation that the younger the star is, the more metals or heavy elements it contains inside the star. So when we observed these ultra-faint dwarf galaxies, we see that they're extremely metal poor, some of them having only, 1,000th or 10,000th of the amount of metal as there is in the sun. So because of that, we were very surprised to see that, they're actually very, very old stars. in these ultra-faint dwarf galaxies. And some of these dwarf galaxies are still around in the Milky Way, as I showed you in that video before. Some of them are still around orbiting in the Milky Way. And because they are still around and they're very close to the Milky Way, that makes them very easy to observe using our telescopes. It's very hard to, observe things that are very far off, because that just, some of them is, attenuated by dust, and then you can't really see them as they are right now. And then it's also hard to take pictures, basically, of things that are very far away, which is why these ultra-faint dwarf galaxies that are our own neighbors are very, they give us very accessible glimpses into the early universe. And okay. So how do ultra-faint dwarf galaxies really help us figure out the origin story of our universe? Well, I would like to start by, this analogy of thinking that the Milky Way is like a city. So what is a city really? A city is just a collection of people coming from all of these different walks of life, all of these different origins. And they all come from different places. They have their own stories, and they move into this big clump or big concentration of people inside a city. And that is kind of what the Milky Way is. The Milky Way was not made as it was. So when the universe was created, the Milky Way didn't just appear like that as this beautiful spiral that we know and love today. How exactly was the Milky Way created? Well, the Milky Way was created in this process called hierarchical merging, which is basically the process where small galaxies merge to become a bigger galaxy, and these big-ish galaxies become merged to become an even bigger galaxy. And how does that process look like? Well, that process looks like this simulation that I show you here, which is one of the simulations that I use in my own research, called the Caterpillar suite of simulations. So what really is going on in this simulation? Well, this is a simulation of the origin of the Milky Way. And actually, let me just drink for a bit. Okay, so what you can see here is from the beginning of the simulation, early on in the history of the universe, there was a small, overdensity of mass, a small clump of mass, and then all of these other neighboring galaxies merged to join that central mass, and then they all join together, and eventually it becomes this huge body that we call eventually became the Milky Way that we know today. And this is the simulation that we use to study the Milky Way. But the problem is, this is a simulation. This is not exactly what happened in the Milky Way, although it can give us an idea about how exactly the Milky Way formed. We don't really know what neighboring galaxies merged to form the Milky Way that we know today. So that is really one of the central questions that we have in our research field, which is that we really want to write this kind of family tree for our Milky Way. What small galaxies and what big galaxies, what bodies formed to become this big galaxy that we know today? And that is, as I said, one of the central questions that we ask. And what we found based on the simulation that I showed you earlier, and this was a plot that we included in my paper from 2022, is that the Milky Way accreted a few big galaxies and many tiny galaxies. So as you can see here in the left bar, you can see that the UFDs colored in orange make up around 90% in number of the number of galaxies that became the Milky Way. So basically, the Milky Way formed because there were a lot of small galaxies and very few big galaxies. But because these UFDs were so small, the number of stars that are in the Milky Way are really predominantly come from the larger galaxies, or what we call the major mergers that form the Milky Way. And that is what is shown on this right bar here, which is that the number of accreted particles or stars are really coming from the larger galaxies. And so this is what I want to show you now, basically, what is kind of an atlas of the Milky Way as a city. What mergers really formed the Milky Way today? So as I showed you earlier, the Milky Way is maybe a neat sphere, but oh, not sphere, like a neat, flat spiral. But really, there's a lot of things going on, a lot of structure, and a lot of stellar streams. And these streams here, the ones that you can see in blue and white, these are all kind of the remnants of the galaxies that the Milky Way kind of swallowed, or what they call cannibalized in some articles out there. And as you can see here, if you look at the Milky Way, you can keep going. This is the center of the Milky Way, and it has, these globular clusters or groups of stars. And if you move forward, they discovered this body called Pontus, which was one of the merger events that happened in the Milky Way. And then this one also, we discovered the Gaia sausage or Enceladus merger. This was the biggest merger that happened in the Milky Way, and they call it the Gaia sausage because when you plot it, it looks like a sausage. But yeah, and then there is also the Wukong merger, the Sequoia merger. And then if you keep going, they also discovered Arjuna and so on. Let's see, where else? So this is also the Cetus merger and so on. So that gives you kind of an idea of all the richness of the history, basically the migration or the merger history that formed, the city that is the Milky Way that we have today. But this is only a very small snippet of the very rich merger history of our own Milky Way. So as I said earlier, we have a very good idea about the galaxies that were accreted by our own, of the galaxies that were accreted by the Milky Way. But the things that we have a good idea of are only the big galaxies. But what about the small galaxies? As I said earlier, 90% of, the number of galaxies that form the Milky Way are ultra-faint dwarf galaxies. How do we form that merger history for the small galaxies? But before I move on, I just want to show you this neat little timeline from Koitzen et al. 2020, where they formed this really neat kind of, as I said, family tree of all the large mergers that formed in the Milky Way. So if you start from the bottom of this plot at 0 look back time, which is you look back 0 years, which is right now. If you keep going up to this, you start going back in time into, the beginning of very close to the Big Bang. So according to this family tree, the first merger that happened was this event they call the Kraken. And then the next event was the event responsible for the stellar streams called the Helmi streams. And then after that, the Sequoia event, and then the Gaia Enceladus event, and then the Sagittarius event. And very soon we will actually be merging with the large and small Magellanic Clouds in, a few billion years. So that will, form the more bottom part of this family tree. And the astronomers that study this field have a lot of fun with naming their merger events like Kraken and Gaia sausage Enceladus. So it's a really fun field. But as I said, we have a good idea about the big mergers that form the Milky Way. But what about the small galaxies? And so how do we form a picture about the small galaxies that form the Milky Way? Well, what we do is we look for the stars of these accreted small UFTs in, the outskirts of the Milky Way. So as I showed you earlier, the Milky Way is this kind of a disk, and at the inside, close to it are the Magellanic Clouds, the large and small Magellanic Clouds. But surrounding the Milky Way is also this kind of spherical collection of stars that are called the halo. And what we do is we look for the stars of these accreted small UFTs in the outskirts of the Milky Way. Why do we do that? Well, partly because it's sparse out there, so it's not too dense. It's very easy to find the stars that we want. And we also do that because it's But yeah, that was basically our main reason why we do that, is because it's sparse. Anyway, so but the problem is that even though the halo is still sparse, there are still a lot of different kinds of stars in the outskirts of the Milky Way. So for example, as I said earlier, there are stars that came from, the main Milky Way itself, not from a merger, which are what we call in situ stars. But there are also stars from the large mergers. But what we really want are the stars that came from these small mergers, that came from these ultra-faint dwarf galaxies. So how can we distinguish these UFD stars, these stars from the UFDs that merged into the Milky Way? How can we distinguish them from the other stars? Well, thanks to this amazing telescope called Gaia, we can kind of start forming a map of the merger history of the Milky Way. And what Gaia does is it surveys all around 1.6 billion stars of the Milky Way, and it basically records their kinematics, which is how they move. So it takes their positions in the sky and then their velocities. And from that, we can form kind of an orbital history, or a history of how these stars move. And as a result of that, we can start grouping stars according to how they move. So a lot of the studies in this area form around this idea that if stars move in a very similar way, therefore they must have come from a similar galaxy. So that is basically what is happening in this plot here. So in this plot which looks at the energy of these stars and then their angular momentum, they find clumps of stars, or stars that are clusters in what we call kinematic phase space. So basically, if a group of stars are clumped together in kinematic phase space, what that means is that they move similarly. Therefore, they must have come from the same UFD. And because and the neat thing that is happening right now is that clumping is an easy thing to do for algorithms. And what previous studies have done is that they look at all these stars from the halo, plot them in this kind of energy versus angular momentum plot, and then apply clustering algorithms to them. And what they find are these clumps, and then they suspect that these clumps are indeed, the UFDs that we have been looking for, and the UFD stars that we have been looking for all this time. But this kind of method was very successful for the big mergers that I told you before, like Gaia and Enceladus. But do they work for these small, much smaller galaxies? So can we trust the algorithms? So that was the question that we tried to address in our research. And what we basically did, as I said, was we took our simulation, and then we plotted them in this energy versus angular momentum plot, and we tested all the different algorithms, the usual algorithms that were used in our field. And so as you can see here in this right panel, you could see that different algorithms group the UFD stars differently, so they kind of give different output galaxies. But this is kind of the correct answer that we have from the simulations that we have. And we found that different algorithms perform differently, but overall what we found was that altogether they still perform very badly at finding the UFD stars. So when I was presenting this poster at the conferences that I went to, the scientists that I met were all saying that, oh, I'm disappointed, but I'm not surprised, because it's just very hard to use these clustering algorithms for such small galaxies. And the crux of this plot is really, if you look at this one here on this leftmost plot, like their recovery rate, which is kind of how many UFD stars they identify correctly, is very close to 0, which is very unfortunate. So that means that we have a long way to go in this kind of study. So one thing that people have been doing is to create their own custom algorithms for these smaller bodies, but we suggested a completely different thing. So as I said, how can we do better at identifying stars from UFDs? And what we suggested is that what we suggested would be the more effective thing to do was to look into what the stars are made of. Because as I said earlier, UFD stars are uniquely old. They're metal poor because they, as I said, they formed in the early galaxy before metals were around. And because of that, they have a unique chemical signature. So but before we can go further into that discussion, how do we really know what stars are made of? And what we do that using this technique called spectroscopy. So what happens really in a star is that when a star burns, it has its own characteristic spectrum. So what does that mean? So when a star burns, it emits light, and light, actually, you can split that into all its different wavelengths, which is what what a prism does here. So a white light is really just light that is composed of light at different wavelengths. And the interesting thing here that happens is that in a star which has a very hot interior and a much cooler atmosphere, that cooler atmosphere absorbs some of the wavelengths of light in that rainbow. And what happens is that it results in some absorption lines. And this kind of thing is what we observe in our telescopes on Earth, which are, the things in this dome on the right here. And so what we do is that we point our telescopes with a kind of prism, and then we split that light up into all of its different wavelengths, and we kind of map their absorption lines. And we find that different stars have their own different patterns of absorption lines, which is basically saying that the stars have their own barcodes. And what we find in UFD stars is that they're known to be low in strontium and low in barium, which is, if you can look at the plot on the right here, the plot on the right says that the green squares are UFD stars, and that they're kind of predominantly on the lower part of this plot, which means that they're low in strontium and barium. And so what we found is that we discovered stars in the Milky Way's halo that have low strontium and barium. So what does that mean? It means that we probably discovered stars that came from UFDs. And we did all of this analysis of their spectra, and what we indeed found that they were low in strontium and barium. And we also found that using Gaia data, we found that they indeed are consistent with coming with a hypothesis that they indeed came from a UFD. And so these stars that we discovered, which is hopefully coming out in a paper very soon in the coming months, our discovery of these stars could offer hints into the origins of the Milky Way. Because as I said, these UFD stars are very old, they're fossils, and then they can tell us about the merger history of our Milky Way. So just to wrap up again, what really am I trying to answer in my research? It's this grand origin question, which is, how did the Milky Way form? And to answer that, we use stars from ultra-faint dwarf galaxies. And I like to think of them as ancient storytellers lurking in the city of the Milky Way. And their motions and their compositions can help us learn about the origin story of our home galaxy, which is the amazing Milky Way. So that is all for my talk today. Thank you very much.
Thank you so much, Hillary. Wow. I can only say, wow, what a beautiful presentation. And it just shows that you are really a great communicator. Thank you for that. Now we will be going to our Q&A, and let me see. It's not related to you. I'll answer this question later, but maybe we can ask our panelists first if you have questions or reactions.
Hi, Jet.
Yeah.
Hillary, I just have a quick question. You didn't address the supermassive black hole that is thought to be at the center of the Milky Way. So what is the role of this black hole in the merger history of our galaxy?
Okay. So what we typically don't look at in our field, we don't look at the supermassive black holes at the center, but there is this known correlation about the supermassive black hole and the galaxies that they inhabit. So what will happen is that when we are in the future, we know that the Milky Way is going to merge with the Andromeda Galaxy. Also, I think there's some feedback. Anyway,
Sorry.
but no worries. We know that in around 4-ish billion years, the Milky Way is going to merge with our neighboring galaxy, which is also a spiral galaxy. And as a result of that, there are our own supermassive black holes at the centers of each of our galaxies will merge into one. But that is in 4 billion years. But our own field really is distinguished by, the kinds of probes that we use. So we could in other studies of galaxy mergers and galaxy evolution, they use black holes, but our field is distinguished by the fact that we use, these old stars or these very metal poor stars.
Any other?
How many billion years again? You said
I think 4
billion years. That's
4
Andromeda.
something.
Virgin
Yes, with Andromeda. But I think before that we are going to merge with the large and small Magellanic Clouds.
Before that, yeah.
Actually, I have a follow-up questions. So another question. You mentioned that you're using kinematics and the chemical composition of stars to identify those that belong to UFDs.
Mhm.
And distinguish them from stars, ordinary stars in the Milky Way.
Mhm.
What other tools can be used to distinguish stars from UFDs and Milky Way background stars?
Thank you. Well, one of the main things that they use is actually spectroscopy and kinematics are really the two main ones, but sometimes other techniques that they use are probably they use distances. So distances obtained also from photometry, but also they also I think use stuff from Gaia as well. And then they also probably use how how bound they are gravitationally. So they probably use some studies of velocity dispersions and so on. But really, in my experience, we've only ever used the most parang telltale signs are really the ones that you can get from spectroscopy and kinematics.
Hillary, do you have any idea how many galaxies out there have supermassive black holes in its?
Yes. So this is actually a very big and a very active question of research right now. So we have found so far that a lot of the galaxies that we've seen, especially the ones that are big, like the Milky Way, they all have their own supermassive black holes. But that's actually kind of an interesting thing to find, in that why do galaxies always come with black holes? So this is still an open question. But so far, from all of our observations, all of the trillions, all of the galaxies that we've seen so far that are big, all come with their own supermassive black holes. So it's kind of an assumption that if you see a big galaxy, there must be a black hole inside it. But not all of them are easily observable. So there are some galaxies which have supermassive black holes that are active. So they have, very bright jets, and we call them active galactic nuclei. But there are also some galaxies that are we call quiescent, which are, quiet and not actively spewing jets. So they're not as bright. But we typically assume that galaxies come with their own black holes.
The reason why I asked that question is, could it be that the black hole is the one that's actually helping in the formation of galaxies?
I see. Yes, well, that's an interesting idea, which I think that could help, but I think because the black hole is such a small, it's not as big of a contributor to the gravity of the Milky Way. So what's really happening is that mergers happen because of gravitational attractions, right? So you have gravitational attraction between body A and B, and usually body A is bigger than B, and then that gets they get attracted, and then a merger happens. And of course, part of that gravity, part of the thing that is helping with the gravity of the Milky Way is its own black hole. But the black hole is actually not that big compared in terms of mass compared to the Milky Way. So I think our own Milky Way is around 10 to the 12 or 11-ish solar masses, but our own black hole is around probably only a million-ish times the mass of the sun. So there's a big disparity between the mass of the Milky Way and the black hole. So the black hole isn't really the biggest contributor to the gravity of the Milky Way. It's different from, the solar system, where the sun has 99% of the mass of the solar system. But in a Milky Way, it's more distributed across the whole galaxy, the mass.
Thank you.
Thank you so much.
We have some questions already here from the Q&A box, and I'll read the first one. By the way, Hillary, I think Lovely Lopez answered the Magellanic Clouds in the chat,
yeah.
Q&A tab, but I was not able to.
Thank you,
that.
Lovely. Thank you.
And then here's a question from Isabella Esquivel. How many UFD do you expect?
Okay.
Do you suspect is there? How many UFDs do you suspect is there in the Milky Way? And how long will it take to find all of these?
Yes, a very good question. So thank you, Isabella. So far, there are around 60-ish UFDs that we have found that are, still existing and orbiting around the Milky Way. So that means they haven't really merged fully with the Milky Way. But in the Milky Way itself, we don't know how many of them merge. And that is what I said earlier, that we really, this is still the big question that we're trying to ask, is that how many of these UFDs merge to form the Milky Way? When did they come and form? How does that merger happen? Do they get stretched in this direction, in that direction? Do they spread everywhere, or so on? So these are still the questions that we're asking. And how long will it take to find all of these? I don't know. So that is, I predict that within the next 10 to 20 years we will have a better idea of how many of them are there, or what properties they have. We can get a much better map of the Milky Way within 20 to 30 years. But when we answer one question, we find another one later, so we really don't know when we'll get to the bottom of this question.
Yeah, okay, thank you. And this is from, wait. I think you answered this already, but the question from Kimnar Joseph Duwat is, how is metallicity, or how is the metallic content of small galaxies measured?
Yes.
Yeah.
So I mentioned it earlier that we use spectroscopy. We look at the star, and then we take the light that is emitted by the star, put it on our telescope, and then our telescope splits it into its different wavelengths, and then we find, as I said, the dark spots in the barcode of the star, and those dark spots tell us about what metals are in the star or are not in the star. So we mainly use this technique called spectroscopy.
Yeah, I like that barcode analogy for the for the spectral lines.
Yeah, they are literally barcodes.
First time I've heard of it. And this is a question from Rafael Arabia. Is there a possibility for our star in our solar system to collide if we merge with another galaxy?
I don't think so. Well, as I
The sun.
mentioned,
Yeah,
as I
will the
mentioned,
sun collide?
yeah, I don't think so. Well, as I mentioned earlier, we expect that we're going to collide with or merge with Andromeda in 4-ish billion years, but there will be no violent collisions in between stars happening. It will just be, kind of like graceful mixing of two liquids. And actually, even though galaxies seem like very dense things, there is actually a lot of space in between stars. So even if we merge with Andromeda and an Andromeda star comes into the Milky Way, there's still so much space in between them that it's very unlikely that they will collide.
Thank you. Here's a question from RV Perez. I wanted to ask this question also earlier, but here's the question from RV. Hi, we met at an event at PTC organized by Mr. Dito Borromeo. Do you use the James Webb Telescope in your research, and are there new telescopes to be launched that will be very useful for your research? Of course, aside from the GIA telescope.
Yes. Yes. So yes, for Sir RV, I remember meeting you at the PTC event. Nice to see you here. But yes, I actually don't use the James Webb Space Telescope for my research right now. I was very close to working with someone who was actively using the JWST, because the JWST also looks at I know someone who uses it to look at spectra of very old stars, and they, want to form a metallicity map of the early universe using JWST. So I was very close to working with them for my PhD, but I ultimately decided to go to a different university. But no, I don't work with JWST. But in the future, there are some very exciting things that are being built. So one big thing that we're very excited about is the Giant Magellan Telescope. So right now, what I'm using for my research is the Magellan telescopes, but there is a giant one coming in around, I think, 2030 or something. And it's around 30 meters in diameter. Meanwhile, the one that I'm using right now for my research is around 6 meters only. So it's extremely humongous, and we're very excited for the discoveries that will come from the Giant Magellan Telescope.
Okay. Thank you. And this is a question from Mark Erickson Kalunod. Could you also use other stars which are not part of the ultra-faint dwarf galaxies to determine how the Milky Way galaxy formed?
Yes. So as I said, there is also another way to look at how the Milky Way formed, and that is, I know there is also another scientist at MIT. His name is Rohan Naidu, and he looks at the bigger mergers that formed the Milky Way. As I mentioned earlier, we have other events called the Gaia Sausage Enceladus, or Kraken or Sequoia, that formed the Milky Way. And these stars are much easier to identify, as I said, because they come from much bigger galaxies, unlike the UFT stars, which come from much smaller galaxies. So they do use these other stars to, reconstruct the origin story of the Milky Way.
Thank you. And this is a more basic question from Honey Rose Manisha. Hello, Ms. Andales. My question is, what makes the Milky Way spiral? I think it's a barred spiral, whilst the UFDs you have shown and other galaxies are not. Thank you.
Yes, this is a very interesting question. Well, as I said earlier, there are different things that this is actually still an open question about what makes some galaxies spiral and what makes some galaxies elliptical. There's still some small questions in that are unknown. So we know that some of the galaxy, the Milky Way itself, is a spiral, but there are also other big galaxies that are elliptical. So they're just like, they don't have that much of a form. Meanwhile, the UFDs are kind of parang just irregular, and I think that has a lot to do with the gravity inside these UFDs, and because the gravity is not strong enough, there's not enough to make it into these neat formations. And a lot of it also, if you also look at the large Magellanic Clouds and the small Magellanic Clouds, they also don't have that that much of a defined structure. So it has to do with the mass and the gravity that makes these structures emerge.
Thank you. Here's an interesting question from Christian Neil Diana. Good day, Miss Hillary. I have read before that UFDs are immensely dominated by dark matter. I just want to know your thoughts about this. Has this property been significant in your research?
Yes, this is actually a very interesting thing about UFDs, is that they are indeed one of the most dark matter dominated structures in the universe. And for me, in my own research, that hasn't been super important because I'm looking at stars and what their metallicities, or what things they're made of. And I also look at the kinematics of stars. So for me, so far it hasn't been important in my research, but I do know of some very close collaborators who use these UFDs, and they use these telescopes or surveys called the Dark Energy Survey to make kind of a dark matter map of the Milky Way. And they also use these UFDs to look at the small kind of the microphysics of dark matter. So we know a lot about how dark matter behaves in the largest scale. So at the galaxy cluster level, but there's still a lot of open questions or conflict about how dark matter behaves at the level of a galaxy or a much smaller galaxy. So that is a very interesting thing, and that I also want to try doing research in, but so far I haven't been doing research on that aspect.
Thank you. I think the follow-up question here is from Rafael Arabia, and I think in a sort of way you answered this already. Do you also study dark matter in your research and consider that it might also be the reason our galaxy formed? So,
sorry. Can you repeat the question?
Do you also study dark matter in your research and consider that it might also be the reason our galaxy formed?
Okay. Well, it is indeed the reason that our galaxy formed. So what happens is that this dark matter is the dominant type of matter, even though we don't really know what dark matter is, but we think it's matter. What we know about dark matter is it has gravity, and that's the most important thing about it that we know for now. And we know that when galaxies actually live in a dark matter halo that we don't see, and everything the dark matter does, the galaxy also does. So if dark matter halos, if dark matter clumps, what we call them halos, merge, then the galaxies that live inside them also merge. So indeed, that's true what you said, that the dark matter is the reason that the Milky Way formed. But we can't see dark matter. We don't even know what it is. So our best the way that I do it in my particular subfield is that I look at the things that we can see, which are the stars and the galaxies that kind of trace or follow where the dark matter goes. So that's what I do.
Thank you. Here's a question from Eric Donato. Good morning po. Could the James Webb Space Telescope's potential discovery of galaxies that seemingly defy current cosmological models challenge some of our established theories about galaxy formation and evolution?
Yes, this is very good, and this is actually an active thing that people are talking about right now, because there's ever since the James Webb Space Telescope launched, some researchers have been publishing findings that they found this galaxy that was born way sooner than we thought galaxies were forming. And this is still an ongoing conversation. We don't know what we're going to find, but we do expect to have our expectations change. So maybe indeed galaxies did start forming earlier. Maybe they didn't. We don't know. But what we do know is that James Webb will, let us see deeper into the past. And what we will find, we don't know, but we're open to having our minds changed about how galaxies form and evolve.
Thank you, Hilary. And here's a question from Christopher Acierto regarding your paleontological studies. Would the discovery of the Milky Way's origin help date the origin of other galaxies as well?
Ah, yes. Let me think. I think I would say yes, because the Milky Way is kind of what we use as a model, kind of a model galaxy. I mean, we use the sun as a model star mostly because it's the star that we have closest, and that's the same thing that we do with the Milky Way. We use it as a model galaxy because it's the galaxy that we live in. But we also do that because the Milky Way seems to be the average galaxy out there for some reason. Maybe there's some observational bias there, but so far we can use the Milky Way up to a fair level of assumption that it's the average galaxy. So if we can figure out how the average galaxy, that is the Milky Way, formed, when its mergers happened, and so on, how do these mergers happen, what kinds of streams are formed, where does the dark matter go, then if we figure that out, the model galaxy, we can have clues about how other galaxies are formed, because as I said, the Milky Way is kind of our model. So in a way, yes, we can figure out the origins of other galaxies if we figure out the Milky Way.
Thank you. Here's a question. I think this is from a fellow astrophysicist, Orisvaldo Salviano Neto. Hi, Hilary. Great presentation. I was wondering if the use of the spectral identity of the stars from UFDs replaces the kinematics method used for the big mergers, or does it just add to it as an extra constraint or constraint?
So they definitely does not replace. They're just additional information that we can use as you said, as an extra constraint. So kinematics alone will not give us that much information. So well, I don't know if it was one or the other, but kinematics alone or spectroscopy alone will not give us a better picture of the formation of the Milky Way. So we want to use both together.
Thank you. And this is from Alfred Anthony Lewis, Austria. Is it possible that the other freely moving black holes to form galaxies, since it is the center of other galaxies? And you mentioned that mass is distributed in our galaxy. Is it formed before, after, or during the formation of galaxies?
Yeah. This is a very interesting question, and it's also still an open question. So there are, as I said, in a lot of our galaxies have their own associated black holes in the middle. But recently there was this very interesting discovery that a galaxy basically, ejected or yeeted its black hole into somewhere else in the galaxy, and that made a lot of news. And this was discovered by a professor at Yale. And so there are indeed interesting things that happen with the central black holes of every galaxy. Actually, wait, where did the question go? That was let me find. Okay. And so is it possible that other freely moving black holes form a galaxy? Well, you can't form a galaxy without stars and without dark matter. So you need all of them together for it to become a galaxy. And you mentioned that mass is distributed in our galaxy. Is it formed before, after, or during the formation of a galaxy? So this is still an open question. As far as I know, we don't know how that actually happened. And this is, I think, a question that the JWST telescope is very well suited to answer, because if we can find black holes very early on in the universe, that means that these black holes are indeed important factors or drivers of galaxy formation. But what we do know is that it's not one thing. The black holes are not the only thing that could drive galaxy formation. It's always kind of a feedback between the central black hole and the galaxy matter that surrounds the black hole. They have this kind of interaction. How that interaction happens, we don't really have a very clear picture. So whether that forms before, after, or during the formation of a galaxy, that's still an open question.
Thank you. This is a more general question from Sila Cave. Good day, Miss Hillary. I was just wondering, how does looking at distant galaxies allow us to look back in time? Are we looking at the past in space?
Yes, this is a very good question. So indeed, if we look at distant galaxies, we look back in time, and that's because light has a finite speed. So if you think about it, if you look, you're looking at your phone right now, right? Or you're looking at your laptop. Even though it seems like you're getting the information instantly, what actually is happening is that the light from your laptop or your phone is traveling to your eyes, and that travel happened, in a fraction of a second because the distance is small. But as you go further and further, if you look at a further object, then the light would have needed more time to travel. So if you look at the wall, you're looking at the wall from further back in time. If you're looking at the sun, you're looking at the sun from 8 minutes ago. So what is happening at the sun right now, we have no idea. But what we know is what happened 8 minutes ago. So if we look further away in distance, then we're looking further back in time. So we've seen, quasars, or these centers of galaxies that are very bright. And they're extremely far, therefore we must be seeing them from a long time ago, because the light needed, all these billions of years to travel from us. So to travel from there to us. So and similarly, if we have and maybe aliens in Proxima Centauri, which is 4 light years away, they don't know that what is happening, that COVID happened. So if the aliens in Proxima Centauri would have no idea, because they're looking at us from they only know us from 4 years ago.
Thank you. Here's another. This is again from Rafael Arabia. Thank you again for answering my questions. Wait. Sorry if I have a lot of questions. In your research about the Milky Way galaxy, would you say that our galaxy originated from somewhere like the Big Bang?
Well, indeed, everything in the universe, we believe, came from the Big Bang. So the Big Bang made a lot of hydrogen and a lot of helium and some lithium, and from that formed the first stars. And those first stars, as I said, they formed, they clumped together and they formed galaxies. So the Milky Way did not immediately come from the Big Bang, but if you look back far enough, it came from the Big Bang. Similarly, you could also say that we as humans came from the Big Bang in some far-fetched way. Yeah, so everything came from the Big Bang.
Here's another closer to home. This interesting question from Dave Justin Bantilan. Hi po, I would like to ask if there's a chance our star belonged to one of the mergers.
Yes. I haven't actually thought of that. That's so interesting. I need to think about that. But it's likely that the sun, our sun, is in the, as I said, the Milky Way is like a plate, and then around the plate is a spherical collection of stars called the halo, and our sun is on the plate. And what we know about the plate is that it's composed of younger stars, and our sun is indeed one of the younger stars. We know that from looking at its spectra and its metallicity. We know it's young, and we know that a lot of the stars on the disk or on the plate of the Milky Way are in situ stars. They come from the Milky Way itself. So maybe it is from our own Milky Way, but I'm not sure. I should Google this.
Thank you. I guess you described this already before, the answer to this question, but I would like to ask this again from Galamay Jonathan. Good morning, Miss Hillary. Is it probable that when our galaxy and our neighboring galaxy Andromeda are in close proximity, they will pass through one another and disregard one another rather than merging?
Yes. So as I think I mentioned this earlier, but when galaxies merge, it's really just, two very wispy things passing passing through each other. It's not like two things that are everything is colliding in all places at once. Just because these galaxies are so big, but there's also a lot of space inside them. So if you have two things that are big and have a lot of space inside them, it's very unlikely that individual stars will, collide. So it's correct that they will just pass through one another, but they will eventually merge to become one big galaxy.
Thank you. Wow, we still have a lot of questions. Is it okay? We should proceed.
Yeah, we can keep going.
I think we have time. So here, I'll ask this first from Bernie M. Hi, Hillary. I'm new to galaxy topics, so I know nothing about it. So I want to know if the galaxy dust is also being used to identify the age of the galaxy. My apologies for this question.
Oh, no. I actually am not sure. So I'm not sure if we have used dust, because for a lot of our research, dust is just an annoying thing that we want to subtract away from our data.
Yeah.
But there are indeed a lot of other astronomers who are actively using dust in their research, and they use, the compositions of dust to look at the supernovae, where they came from, and so on. So I could imagine some people using it to determine an age. But personally, I am not sure about how they're doing that because I'm not in that field. But if you message me later, maybe we can talk and look for resources.
Thank you. And the next question is from Dave Noah Edward Baluyot. Hello, Miss Hillary. Just curious, how far back in time has your study of the galaxy reached? Like an approximation.
Yes. So in my study, I only look at really the things that are around the Milky Way. So maximum around few thousand or few 100,000 light years. So that's really the things that I look at. They're around the Milky Way, they're close by. But I know other astronomers who who are more interested in the large scale structure of the universe, and they go back millions of light years away. We say gigaparsecs away, gigaparsecs away. So those are very far, but I stick to the neighborhood of our home galaxy.
Thank you. I don't understand this question, but I'll read it now from Daniel Romasok. Hi, Miss Hillary. With the recent news about UAP, would you say it is true? Have you seen one hovering in galaxy when you look in the telescope?
I'm not
Thanks.
sure. I think are the UAPs the ones that are the parang bagong term about UFOs?
I don't know.
Yeah, they were doing a panel about this in the US, I think, but I don't know. I don't think about UAPs ever. And I am sure that we have not seen any through any telescope. So I don't think so. UAPs are very there's not much evidence for them, so I don't believe.
First time I've heard of that term, UAP.
Yeah, it's very new. They started using that term very recently.
Oh. And this is again, I think, from our lay attendees. Hello from Rommel Espora. Hello, Miss Hillary. I was wondering if string theory is true. Will it have a significant relation to the formation of galaxies such as the Milky Way?
I see. Well, that is very far from the scale that I study. So as I said, I study things at the galactic scale. Meanwhile, string theory looks at scales at really the fundamental core of matter. So subatomic particles scale, and that's very small. And what string theory does is it tries to find what is the nature of matter at its most fundamental scales. Is it if you keep going, cutting it down, cutting an atom apart, where into the smallest and smallest pieces, what do you get? Do you get a string? So that is what string theory is trying to find. And for us, we kind of take it for granted already. So whatever we find in string theory, I don't think it has any implications because we're already assuming that this is how matter behaves. And matter has, you know, matter has gravity, matter has electromagnetic interactions, and we take that for granted. For us in astronomy, that is an assumption that we just use and we don't think about. Meanwhile, for string theorists, that is an active question. So, but whatever they find, it will change what we think, but not fundamentally, because we are already using the properties that we currently observe. So no, nothing I think major will change in terms of astronomy, but it will change how we think of how matter works.
Thank you. This is a question from Joshua Jewel Palolan. Good morning, Miss Hillary. Is Earendel actually a star or another galaxy?
Yes, I just saw the latest news about Earendel. So Earendel is what JWST recently imaged as the oldest star that we found with JWST, or oldest star ever that we found. And I think based on my reading, it is a star, and we discovered it by using gravitational lensing. So there was Earendel, this very old star from, you know, light years and light years away. But then in between us and Earendel, there was a massive galaxy cluster that was lensing the star and also the galaxy that it lived in. So I think Earendel is just a star, and its galaxy was also lensed as well.
Thank you. Here's a basic question from one of our attendees, Erica Stanla. Valencia. Erica Shania Valencia. Hello, Miss Hillary. How do you like date stars and galaxies? Is it through their color?
Kind of. So you do date them through their color and also through what they're made of. And the principal way that you use that is, one of the ways that you do that is, as I said, through their spectra. And as I said, the spectra is like their barcode, and by looking at the specific barcode, you can kind of guess their age. But another way that you do that is through photometry. And basically you take a picture, you take a camera which is on your telescope and you put a filter on it, and the filter only lets in specific wavelengths of light. And you take a camera, put a filter on it, and then you take a picture of the star, and then you put another filter on your camera, and then you subtract those colors, and then you kind of get the color of the star. And by looking at stars and their colors and how bright they are, you can approximately get an age for them. And another way that you can age stars is also through astroseismology, which is a very exciting field. So from the word astro, star, and seismology, quakes, from looking at how a star quakes or vibrates, you can kind of see how old it is. I'm not in that field, but it's very cool. But apparently you can use those to also age a star.
Thank you. Here's another question from Rafael Arabia. This is my last question related to my first question. If the galaxies merge, doesn't it affect the gravitational curves of stars and planets inside the merging galaxy?
I would predict that, as I said, they don't collide. Things wouldn't collide just because you have a lot of space in between individual stars. But what would collide, or what would affect, the gravitational curves, are if you have huge bodies of gas between Andromeda and the Milky Way, and they would collide. So you could have different, when those masses of gas collide, you could have new stars forming. And so that would affect the gravity of the inside. And another place where the gravity would probably be changed is the core of the galaxies, which is what we call the bulge. And so as a result of that, all of the gravity, how the gravity is configured inside the galaxy would be changed. It's just that there's no individual collisions that are happening, except for the gases.
Thank you. Thank you, Hillary, for your patience. Can we ask a few more questions?
Oh, yeah,
Is it
of course.
okay? This is from Yvonne Hommel. Hello, Miss Hillary. I just want to ask, can you use GIS or Geographic Information System technology in space exploration? He has been asked, yeah. On Yvonne Hommel, yeah.
I don't use GIS, and I don't. Well, GIS is a technique, I think, as far as I know, specifically developed to study Earth,
Yeah.
using satellite imaging. So you can't really use that to look into space. But the main principle that GIS uses really is remote sensing, right? And so basically what remote sensing is that it you send an instrument away from you, and then you use that instrument to look at things for you. And we use that everywhere in space exploration. So when you're looking at Mars or other planets, Jupiter, or the moons or asteroids, or like I think we also did that through a nearby asteroid. We use remote sensing all the time. So not GIS specifically, but definitely the idea of remote sensing is everywhere in space exploration.
Thank you. Here is from NK. Hello, Miss Hillary. I read an article about controlling quantum energy fluctuations in empty space days ago through Physics World by optic researchers in the US. I was wondering about how it will change the way we look at astronomy in general, especially in determining their ages, as we base them on the energy emitted, for example, stars. So about quantum energy fluctuations in empty space. Yeah.
I don't think it will, as I said, this is kind of the same thing as the question that was for string theory earlier, in that they're very different scales. As I said, I look at the Milky Way and it's like 10 to the very huge number meters in scale. Meanwhile, these things are at very minute subatomic scale, smaller than an atom. And whatever we find in those places, in studies from those fields, don't really change how we look at astronomy. Because the questions that they're trying to answer are the assumptions that we have, basically. But the assumptions can change, but I don't think it will change drastically in terms of how we do astronomy in general.
And this is from Toring Kent. Hello, Miss Hillary. Could you explain how simulations and models help us understand these celestial bodies from the early universe? How do scientists create accurate models and use them to validate findings against observations?
Yeah.
Good question. Yeah.
So this is a very good question. And indeed, we use simulations and models a lot to figure out what the universe is like, because in astronomy, we can't do experiments. So in other sciences, you can do experiments where you have two things in two different conditions and you see how differently they react. But in astronomy, you can't really manipulate a galaxy. All you can do is watch and wait, or just you can't even wait, you just watch many different galaxies at once. So as a result of that, what we have to do is a lot of astronomy is driven by studies using cosmological simulations or computer simulations, and they also do models. And basically what these simulations do is that they start with a set of parameters, and the parameters are basically, the recipe that you use for the simulation. And however you change, they're not the recipe, they're more like the ingredients. So if you change the ingredients a bit in the simulation, then the output of the simulation will change. And these, how we look for these parameters are, we try to find them from observations. So for example, the simulation that I use, the caterpillar simulations, it uses parameters from the WMAP satellite, and actually no, the Planck satellite. And what the Planck satellite, which was floating up in space, whatever it measured, we use it for our simulations. We plug that in, and then you basically run the simulation, and then you now have a simulation of the Milky Way from the early years, very close to the Big Bang up until now. So that is one way that we can study, we can use simulations to study the universe, because we can't do experiments. And then models, also models and simulations are kind of, they're very much interacting. They have this own feedback. They have their own feedback loop of, if the model is basically kind of a theoretical, our theoretical understanding of how things work. So for example, we have models about how supernovae explode. We have models about how galaxies merge or how galaxies evolve in time. And these models are primarily the work of people working in theory, and whenever the models get better, the simulation gets better, and when the simulation gets better, we find new things, and then maybe that also helps make the models better. But ultimately, what we're looking for is also observations, confirmation through looking through the telescope, which is really what's out there, what's real. And all of these three are interacting so that we can ultimately find what is, we can finally make a clearer picture or a better understanding about how the universe works. So everything, all of it is interacting: simulations, observations, and models.
Thank you. Thank you for that answer, Hilary. I have to ask this question from a doctor friend of mine, Dr. Dick Andales. At the time the Milky Way and Andromeda merged, at what stage is the life of the sun then? What would be the condition of the Earth then, and what would happen to Earth in terms of supporting life as we know it?
Well, by the time that Andromeda and the Milky Way merged, sun would have been long dead. So we expect that the sun.
So that would be more than 4 billion years. More, yeah.
Oh yeah.
How many years? Yeah.
Actually, let me confirm.
At least a billion.
Yeah. So
yeah, sorry for interrupting. Thank you.
Yeah. Because we expect that the sun, and we know that the sun will become a red giant and then a white dwarf, and then in the process of becoming a red giant, it will swallow the Earth, even beyond the Earth, as a result of that. So everything will be destroyed. And so probably by the time that the Earth, by the time that the Milky Way and Andromeda merge, we will be all gone, unless we figure out how to live in a different star.
Thank you. Here's a nice question, an interesting question from Dennis Marquez. Hello, Miss Hiller. Can you describe the true color of our Milky Way galaxy based on your observation? Can you describe the true color of our Milky Way galaxy based on your observation?
The true color.
Yeah.
That's hard. You can't really have a color of a Milky Way because it's composed of many different stars. But you can do that for other galaxies if you observe a faraway galaxy and you point a telescope at it, then you could use photometry to figure out what the principal colors of that galaxy principal colors of that galaxy is. Yeah, basically. But since we are inside the Milky Way, we can't do that. You can only do that for galaxies that are far away and that we're outside of. So yeah.
Thank you. This is a more a little bit personal from RV Perez. Hi, it's me again. Just curious, what specific topic are you currently focusing on in your research? Do you work by examining the readings of Gaia, GAIA, or do you still look at the stars at night?
Yes. Okay, let me read the question. So for my research right now, I am using Gaia. I'm using the data from Gaia, but in the future in my PhD, I expect to also look at data from the Sloan Digital Sky Survey, which is another telescope that is looking at many stars all at once, and that's going to revolutionize astronomy as well. So, but at the same time, I will also use telescopes and look at the stars at night, because that is what I find fun. So I could have totally chosen a different path where I did computational astrophysics, but because I really liked my experience in my classes, as I mentioned, in Spain and in MIT, I really want to keep doing the conventional looking at the stars astronomy.
Thank you. Maybe I'll just read the last 2 or 3 questions. Thank you again for your patience, Hillary. And this is from Kyla Pines. Hello, Miss Hillary. Could you please provide information about neutron stars? Are there any estimates of how many neutron stars are there?
Okay.
So she's interested in neutron stars.
Yeah. Well, yeah, neutron stars are some of the most interesting things. So what happens when you have this very massive star and then it dies basically after becoming a supernova. And sometimes you have, after a star blows up and becomes a supernova, you have the husk of the original star, and that is in the form of a neutron star. And it's called a neutron star because it's a lot of it's extremely dense, and it's basically made of neutrons. And they're extremely interesting, and sometimes we observe them to have kind of very powerful radiation jets, and that they're what we observe them as pulsars. And we don't really know how many neutron stars there are, but we know that in UFDs, in an average UFD, you can probably find them in like 1 neutron star in 5-ish UFDs. So, and actually no, 1 neutron star merger in 10 UFDs. But on the count of how many neutron stars there are, I actually don't know. But that count depends on how many massive stars there are. So that count depends on how many young stars there are in your galaxy, probably. So I don't know how many there are, but you could probably look that up somewhere if you want to talk later.
Thank you. And this is again another question on dark matter from Glenn Amita. Could neutrinos be the missing dark matter?
Yes. The answer probably is no. They asked this question a long time ago, and they basically did this investigation where they counted all of the possible sources of neutrinos, and there is simply not enough to account for dark matter. But they are looking at other types of things that could be dark matter. So they're looking at these things called WIMPs, called weakly interacting massive particles. And they're also looking at another type of matter, which is called an axion. So though there are many different directions that could lead us to finding what dark matter is, but so far we've basically decided that it can't be neutrinos.
Thank you. If there are no more questions, I would like to end this Q&A with the 2 questions about I think these are being asked by students or those who are interested in astronomy. And one is from Erich Donato. Any advice po for astronomy students, especially for aspiring astrophysicists? Thank you po. And from Joshua Joel Palolan, can you imagine the future of astronomy here in the country? The future of astronomy in the Philippines. So advice for aspiring astronomy students, especially astrophysicists, and is there what is the future? Can we see the future of astronomy here in the Philippines?
Yes.
Yeah.
Thank you, Erich and Joshua, for the questions. So I want to answer Joshua's question first, in that the future of astronomy in the Philippines is very bright, mainly because the community is coming together more as a result of, I think a lot of it has had to do with COVID, and because COVID normalized. COVID was many bad things, but one good thing that came out of it was unifying communities together. And like, like me being able to bring this talk to an audience in the Philippines is one way where we're bringing people together. And I know that the community of astronomers in the Philippines is also coming together. I'm currently part of a group of, astronomers that are part of the diaspora, or also Filipino astronomers that grew up in the Philippines. Na we're trying to build a program for young aspiring astronomers where they can learn research. And so that is one positive thing. And then there's also, from just from what I know from my immediate circles, I know that the groups of Dr. Reyna Reyes and Professor Ian Vega, they're both doing very good research in terms of using survey data and data science for astronomy. They're also doing gravitational wave astronomy. And I expect that there will be a lot more to come. And I don't even know, the breadth of the astronomy interest in the Philippines. So there's a lot of good things happening right now, especially in terms of keeping the community together. So there is a bright future, although you need to do some work to find the community. But communities like Astronomical League of the Philippines, Philippine Astronomy Forum are good places to start. And that brings me to my to the answer for Erich's question, which is advice for astronomy students. And my main thing to say would be to really find a community, because without a community, it's hard to keep up an interest if you can't find other people who share your interest, who nurture and inspire you to, keep digging deeper, keeping your curiosity alive. So number one is find a community. And then number two is, keep your curiosity up. The good thing right now is that there are a lot of resources that you can find online by yourself, just from YouTube. A lot of the astronomy I learn is just from YouTube and just, going on Wikipedia rabbit holes. So you can find a lot of these resources online. But if you really want to pursue astronomy professionally, then you would need to find a mentor. So that is my third piece of advice, which is for young students that are aspiring to really pursue astronomy professionally, is to find a mentor. So find places that have astronomy programs. And in the Philippines, I know that, Rizal RTU has an astronomy program. I think New Era University also has a program. And NIP, Ateneo, the NIP in UP Diliman, they have professors who work in astronomy. Ateneo de Manila has a physics program. So all these places with physics programs and professors who work in astronomy are very good places to find mentors. And actually, just yesterday, I talked to a student in Ateneo de Davao University. They were studying aerospace engineering, and they got time at an observatory network. And so these are just places where you can find mentors. So yeah, that's basically all of my advice. Find a community, keep your curiosity up. And if you really want to pursue astronomy professionally, then find a mentor, ideally inside in the Philippines, but you could also actually cold email people. So this is what I've done a lot in my career. I don't really have a career yet. I'm barely starting. But what I did for many years was I just follow someone on Twitter. This was back when Twitter was cool. And I would find astronomers or PhD students that I liked. I asked, and I'm curious about the research. I just message them like, hi, I think your research is cool. I want to learn about how you got to your path. Do you want to, possibly set up a call or something? And it's always surprising to me how helpful they are. So that's my other advice, which is to find people, find role models, and maybe even, strike up a conversation, because for me, it has always gone well. I've always found some good mentors just from messaging people on social media. So, but just remember to be nice and polite and respectful of their time. But besides that, you'll find some good people from doing that.
Thank you so much, Hillary. You're the perfect role model for them. Aside from before there was Dr. Raina Reyes, now they have you.
Wow.
Thank you so much for this talk and for inspiring our students in physics and astrophysics. Before we end the Q&A, maybe I'll ask our panelists again for any last comments or questions.
Just two things. You asked the question, UAP, it's a new term. Yes, Hillary's right. It's unidentified aerial phenomenon. It used to be called UFOs.
Phenomenon. Interesting.
And then for the viewer who asked the question about the color of the Milky Way,
The color.
I think you can Google it. I used it in my slide presentation before, from the Earth to the stars and back, which is the multi-wavelength Milky Way. Because if we talk about color, we're talking about visible light. But what they did was, I think it's NASA Astrophysics Division or something that did this, and they had the Milky Way in multiple wavelengths. Yeah, so if you try to find that poster, it's really cool. Are you familiar with that, Hillary? Multi-wavelength.
Oh,
Milky Way?
yeah. Well, it's right that it is multi-wavelength, and that makes it even harder to find a color, because
Yes.
in astronomy, things really don't have a color because you look at them in multiple wavelengths. And the way that we measure color in astronomy is you take a picture in one filter and then take a picture in another filter and then subtract them. But that's not really what color is in our eyes. That's not how our eyes work. So color is a tricky concept in astronomy. But we use different, as in indeed, multi-wavelengths.
Yeah. Color is based on what we perceive, what our eyes perceive.
Yeah.
But in reality, I mean, even other animals in our planet don't see colors the way we do.
Yeah.
Does Andromeda galaxy have a color? Does it have a color that we can describe? Like the Milky Way? No.
It's this kind of the same thing that it is you have to see it in multiple wavelengths, and then
Jet.
It is, I think it is blue. Predominantly, I could kind of say it's blue because the light is blue shifted, but that's not really what makes it blue. It's not exactly blue. So it's very hard to describe one color.
Okay.
Edwin, you were saying?
Yeah, Jet, if I may ask, probably the final question for the evening.
Okay.
If I can have the honor. So Hillary.
Okay, yeah, please.
I'm just curious. You were talking about dark matter, dark energy earlier. And my question is, let me know if this makes sense or not. Einstein's, most famous equation, E equals mc squared. That applies to ordinary matter. And we've proven that with, nuclear weapons and nuclear energy. Now, can that equation apply to dark matter and dark energy also?
Of which we don't know much about.
Because you said you don't know much what dark matter or dark energy is. Is there a similar, equivalence that governs these things, dark matter, energy?
Well, a lot of I'm not sure how to go about this question. Well, the only things that we know from dark matter is that it has gravitational interaction. So dark matter, for all we know, does, according to our assumptions of dark matter, it obeys general relativity, because which is another one of Einstein's equations. And but for the matter and energy equivalence, I'm not sure if we typically use that kind of equivalence, because to do that, you would have to look at the momentum of the thing, and then the speed of light as kind of a multiplier. And I'm not sure how you could go about that, because we don't even know what dark matter is as a thing. The only thing that we know it is as a clump of things that we don't see but affect the things around it. So it's easier to think of EMC squared for the in the notion of individual atoms, where we have, a notion of energy and a notion of mass, and then the speed of light squared is just the multiplier for that. But I'm not sure how you could apply that to dark matter exactly.
Thank you.
And it would not be fair to use the speed of light squared as a constant factor, because it's dark. It doesn't have photons.
Yes, but also I think that the way that we think of energy is different.
Yeah.
I think, for dark matter.
So we
but
need
I
another Einstein.
Yeah,
for
we
that.
need another Einstein to come up with a new equation for dark
Well,
matter,
before, yeah,
dark energy.
Edwin, thank you. But siguro, allow me to ask from the point of view of a non-specialist. I mean, I'm a non-physicist, no? And I read somewhere that Hillary is very nice. I see your passion in your work, and that you are working in a field like astronomy, wherein you can really see the what they call that, the merging of these models and then theories with observation. But I read somewhere that is it really like when I read about the string theory and all those things, there's a criticism now about the way physics is being done, that we're going too mathematical,
Yeah.
that it's too, and to the point that sometimes you cannot really validate this with observation, because it's all too mathematical, like string theory and so on.
Yeah.
What is your idea about this field, especially for those who are aspiring to go into this field, aspiring astrophysicists?
Yes, so this is indeed a common criticism of how string theory is going. So a lot of string theory is motivated by the beauty of math, and a lot of it is actually in the beauty of symmetries. So a lot of I met some physics. When I did the Breakthrough Junior Challenge, I went to the awarding ceremony, and we had this dinner with physicists and mathematicians. And then the mathematicians started talking to the physicists, and they started talking about what the mathematicians thought about string theory, which is very interesting that they were interacting in this way. And the mathematicians all said that, oh, string theory is such a beautiful theory. Imagine that kind of agreement between people in disparate fields, and that just is kind of a hint in how intertwined the math is with physics at the level of string theory. And as I said before, the way that string theory is driven, at least according to some critics, is by looking for the beauty in math. They're not unlike astronomy, which is developing models or developing different theories about galaxies and stars by looking at observations, or by looking at observations, and then that informs the simulations and so on. But in astronomy, really, we're driven by observational data. But in string theory, what is happening is that the realm at which you can investigate string theory is at such high energy levels that we don't reach them with our current colliders. And to probe, you know, the energies to start validating or getting the experimental data to investigate whether string theory is true or not, you would need these billions on billions of dollars to build those colliders. And this is the criticism, that it's hard to really find the experimental support for these theories. And a lot because it's hard to find the experimental backing for string theory. A lot of it relies on the mathematical beauty of the theory. And the way they do it is they just, you know, find these symmetries, or like, if this thing is true mathematically, there must be some symmetry that we can find, you know, some kind of. And that kind of argument is not motivated by data. That kind of argument is motivated by some kind of sense of aesthetic beauty. And this is really where the criticism comes from. Because it's just so hard to find to reach the energy levels to probe these theories. We're kind of resorting to math, and that has made some people lose trust in string theory.
Thank you, Hillary. It's late already there. So let me thank you again, and for inspiring everyone, for inspiring us, not only the young ones, but also us, the older ones. You're really, truly with your beautiful lecture and the way you communicate, it's really gives us even in our other fields, it makes me more enthusiastic with our work. No? So for this, we would like to present you our ALP Certificate of Appreciation. And this certificate from the Astronomical League of the Philippines, I would like to read this. This is presented to Hillary Diane Andales for her invaluable insights, experiences, and expertise shared with the participants of the online talk entitled Searching for the Oldest Stars and Galaxies in the Universe, held as part of our ALP Astronomy Experts Series of 2023, given this 30th day of August 2023, signed by the President, Mr. James Kevin T., and yours truly, Dr. Jose Francisco Aguilar, Vice President. And before we go, Hillary, can we take our customary group picture?
Yeah, of course.
James, gallery view. There. James, you're muted.
Sorry. Wait. Ready? 1, 2, 3. Wait. 1, 2, 3. 1, 2, 1, 2, 3.
Oh.
Wait. 1, 2. Last one. 1, 2, 3. Thanks. Thank you, Hillary.
Thank you both. Thank you.
Thank you.
Hillary, I just want to thank not just you, but I hope they're listening tonight. I want to thank your parents and your teachers in school and your professors and all that mentored you, because you won't be here today if it wasn't for them.
Exactly.
I want to thank all of them.
Thank you.
Thank you. At saka, maybe, hopefully, this is not the last, so marami pa. Thank you.
Thank you, Hillary.
Thank you so much.
Hillary, thank you.
Thank you so
Hillary,
much, Hillary.
take this opportunity to announce to our viewers that you're going to be a part of the organizing committee now.
Yes.
Yeah.
Okay, great, wonderful.
we will
Nice.
continue with this.
Yeah.
So before we end, before we conclude this webinar, I would like to again, of course, thank all our attendees. We had more than 100 actively watching all the time, and we have, I think, hundreds also in our live streaming. No? And I would like to thank all of you for joining us. We will be sending your certificate of attendance by email. And as mentioned earlier, this is the 80th webinar of our expert speaker series. Our first speaker was the late Dr. J. Pasakov, who was with us last April 23, 2022. And our other esteemed speakers since then were Mr. Zolt Livey, Mr. Joe Rayo, Mr. Fred Espenac, Mr. Robert Reeves, Mr. Ken Crawford, Mr. Dave Eicher, Professor Matthew Barlow, Mr. Scott Roberts, Father Christopher Corbawi, Mr. David Levy, Mr. J. Kelly Beatty, of course, Imelda Joson and Edwin Aguirre, Dr. Daniel Green, Dr. Heidi Hamel, Dr. Deborah Emil Green, Brother Robert Mackey, and our last time we had Brother Guy Consolmagno of the Vatican Observatory, and of course today, none other than Miss Hilary Andales. We are grateful to all our webinar speakers who very generously gave their precious time to share their knowledge and expertise to the world amateur astronomical community. We can never thank you enough. And for those who missed our previous ALP Astronomy Expert Speaker Series as well as this one, you can view the video recordings of our past webinars at your convenience at our official ALP YouTube channel as shown here. And the next online talk for our ALP Astronomy Expert Speaker Series will be on September 17. That is a Sunday at 10 a.m. Philippine Standard Time, or on Saturday, September 16, Eastern Daylight Time, 10 p.m. We are currently at solar maximum, so that is the period of maximum solar activity, and our esteemed speaker will be none other than Dr. Valentin Martinez Pilet, who is a solar physicist and the current director of the U.S. National Solar Observatory in Boulder, Colorado. The NSO operates America's solar observatories such as the 4-meter Daniel K. Inouye Solar Telescope in Hawaii, the McMath Pierce Solar Telescope at Kitt Peak, Arizona, and the Richard B. Dunn Solar Telescope at Sacramento Peak in New Mexico. We will be posting our final small announcement for the talk at our Facebook page and at the webpage of the ALP, astroleaguesfields.org. And for our panelists, I will send you the link to our post-webinar meeting after this. Thank you, everyone. Clear skies and keep safe, everyone. Stay healthy.
Yeah.
Bye-bye.
Everyone.
One
Thank
more.
you, Hilary.
To
Bye
all
now.
the viewers, since Hilary is joining us in the organizing committee, to all her fans, we hope you can join us every month.
Okay.
Yes.
Thank you.
Thank you.
Thank
Bye-bye.
you.
Bye.
Good
Bye,
morning.
everyone.
Bye.
Good night.